This conference will now be recorded.
Okay, welcome to this lecture. Now we are going to discuss today general Poisson Q part second. So far we have given the basics of the general Poisson Q or the Poisson Qs with Qs with Poisson arrival. So lastly we will see the nature of the expression for Pn. So main purpose of conducting this process or studying the general Poisson Q is that we are going to have the closed form expression or the simplest form expression for the probability of n customers in the system. Now it has been very much clear, crystal clear that the Pn does not depend on the time t. This has become free from the time t. Why? Because we are discussing the problem under the steady state. So last time, if we revisit and reminisce that the previous lecture, then the n state of this queuing system is n, meaning thereby it has n customers. This can move into states. Uh, are you getting my voice?
Yes, sir. Yes.
Okay. Okay. So in this way, I am just revisiting the previous concept in a hurried manner that we can move from state n to n minus 1 and n plus 1. Its interpretation I have already given. So now what is happening? I was discussing this figure. This is the most important figure. Once more, I would like to have a visit, have a scene of this picture. You look at this picture. This is the general. This is the general one. This one is general state, as I explained. And this n can move from n to n plus 1 and n minus 1. Similarly, these are the particular cases 0, 1, 2. So 0 state is the smallest state. 0 state is defined in a manner that it has no arrival, it has no customer. So how we can interpret this situation of no customer? We interpret and justify the situation that we are going to begin with, we are going to start, or system is going to be booted right now. So 0 is okay. So can we interpret the minus 1 state? Minus 1 state is not defined here. How? Because minus 1 number of customers is available in the system is not justified here. So I was yesterday in my previous lecture, I wanted so this transition states, but I could not complete, and therefore I am completing this interpretation again, explaining this situation again. What is happening here? 0 to 1 means you look at 0 is state. We are moving from 0 to 1. So we can move the state 0 to 1 from state 0 to 1 only because of one arrival, and therefore arrival rate is here. So the state from where we are moving, it is a suffix in the rate. Here it is service rate, so there is no departure and therefore there is no service rate. Now just reverse case 1 to 0. 1 to 0 means we are in the state 1 and moving to 0. It means that without departure, this is not possible. So departure rate is here, but arrival rate is not here. So departure rate is what? From where we are moving? We are moving from 1, and therefore this suffix is taken from the beginning state. I mean from where it is originating or stemming out. Now 1 to 2 similarly, arrival is lambda 1, 1 is here and 1 is here and no service. Similarly 2 to 1, reverse gear, in this case no arrival, and here departure is service rate is taking place, 2 is here and 2 is here. Similarly 2 to 3 and 3 to 1, T3 to 2. You look at here n minus 1 to n. Because of one arrival, it is arrival rate is here, there is no service rate. And n to n minus case is reversed. This happens in reverse manner. So here is no arrival, but here is mu n. Why n? Because it is n here. N to n plus 1, we are moving from n to n plus 1. So arrival is reason here. There is no departure, so no departure. Why this is n? Because this is n. N plus 1 to n, this is reverse case happens here, and therefore no arrival, and there is service rate only, and this service rate is n plus 1 because this state is n plus 1 from we are moving to n. So in this way, this transition diagram has its own justification and interpretations, by which we will discuss the mathematical structure of this digestion, this transition diagram of the transition. So look here, this part mu naught is not defined. I have already expressed. Once more, I am going to discuss mu naught is not defined. Lambda naught is defined, but mu naught is not defined. Mu naught, if we want to define the mu naught, how we can make the situation, make the events happen, how we can make it happen? We can make it happen because 0 is the state, and if we move from 0, then and only then 0 will take place here. You please, this is worth noting here, very worth noting here. You take this note, a special note. 0 means lambda naught, sorry, mu naught means moving from naught. So moving from 0, then you will get 0 here. So you will move from 0 to where? 0 to down, because a death is taking place. So first point is neither you can go to -1 nor any death is taking place here. If there is no arrival, then how death can take place? We cannot define and interpret the mu naught, and therefore this is not defined. The transition diagram is not possible because state -1 is not defined. That is one reason. Even if we allow to take place mu naught, but there is no reason of mentioning this logic. Even mathematically this is shown to be justified, but technically speaking, at this point of the time, even if it has no customer, 0 customer, then how the death can take place? Unless departure takes place, we cannot move from here. So departure is not possible. Death is not possible. Service is not possible because there is no customer. Therefore, mu naught is not defined. Otherwise, you may have confusion in the mathematics that why it is not happening. Okay, now come to the another logic. That logic that logic which we are going to discuss here, that we are going to compute two rates of flow. One rate of flow is into the state or towards the state, and another rate is outside the state or outward, toward and outward, or into and out. Into or out of, there are two terms. Suppose there is a state n, there is a state n here, and here. So whatever arrivals are possible here, suppose this is arrival and this is shown. This is called into state. This arrival is into state. This is term is into, into state. Into state n under state. If it is going, departure is taking place, departure, so arrival is coming here, and then departure is taking place, means departure will be going like this. Departure. So this is called out of state. This rate is out of. So there are two terms and dot, 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 dot. There are two terms, one out of state and another is into state. You remember for the mathematics. So for computing these rates, particularly we are going to compute the expected rate. Expected means here, since arrival is random, therefore we cannot talk about the average. In place of average, we talk about the expected rate. Expected rate of flow of customers. Ultimately, we have to keep in mind that we are going to have a figure in terms of the customers. But here we are taking the rate, expected rate of flow. Rate, why this rate? Because lambda is the rate and mu is also rate. Therefore, here the variable is what? Here variable is the rate. Here lambda is being what being taken, rate is being taken as a variable. Rate is being taken as a variable. So if you remember, expected rate of flow into state, you look at here, into state here. Into means how many into? Into means coming to. So how we get this one? Lambda n minus 1 into pm. Okay. You look at this figure. This figure n. How many? Lambda n minus 1 is the arrival rate. Another arrival rate is here.
Yes, sir. Mu n plus 1.
Lambda n minus 1 is arrival rate, and departure rate from here mu n.
Yes, sir.
Okay. Another arrival rate is here mu
n plus 1. Yes, sir.
Departure, but here it is arrival. Here it is arrival. Here it is
Yes, sir.
arrival. So there are two arrivals and there are two departures. One departure is this one out of state, and this is out of state.
Yes, sir.
Arrival is this one, and one arrival, another is this one, and this is the departure. It is going from here to here. and this is from n, out of n, this is also departure. So 2 departures and 2 arrivals. Rates, both are rates. So if you revisit your concept of mathematical expectation, do you remember the concept of mathematical expectation? Mathematical expectation, probability, what we do? This is the case of average, and mathematical expectation is we compute the expected value. We compute the expected value. This was a random variable, value of the random variable x, or you can also put it capital X, no problem, x, and value, how we do it? The value of the random variable x1, the first value, and corresponding value of p1. How many times? Similarly x2, and p2, so forth, so on. How many times? Up to n. Pn, xn into pn. This is the mathematical expectation, and this is the expected value, and this is the average. This is the average, and simply it is written that pi sum over, this is sum I over I is ranging from 1 to n, and pi xi into pi into pi. So here we are also going to compute the expected rate of flow into state n, meaning thereby rate is what? Rate is this one. Lambda n minus 1 is a rate. This is just being treated. This is just being treated as the random variable x. This arrival is random, and corresponding to this probability, without probability this cannot take place. You know that this is random, so random means probability. So corresponding probability is Pn minus 1. In that diagram, if you want to mention, you can mention, otherwise there is no problem. And mu n plus 1, and corresponding probability is Pn plus. This is the inflow. This is inflow. Expected rate of inflow. Similarly, examine the expected rate of flow out of the state n. So you remember this point, out of the state n, and into, you just look here into the state n. And this condition is very, very important, provided n is greater than 0. Okay, this condition is true. Then under steady state, what happens under steady state? Steady state is nothing else but the state of equilibrium. State of equilibrium means the arrival and departure more or less, or on an average you can say, arrival and departures are same in case of the steady state. Means system is moving smoothly. It means that whatever arrivals are coming, they are getting the service and they are departing from the system. Therefore, in this state of equilibrium, A and B are equal. Both rates are equal. This implies what? A is equal to B. A is equal to B means this part, left hand side and right hand side, they are A and B. They are equal. This is called or known as balance equation. This is a balance equation. C is called a balance equation. And this will be used to discuss the problem further. Okay, after getting this balance equation, I hope you may have got this idea that inflow and outflow. They are the expected inflow, expected outflow. Outflow is also customer, inflow is also customer. So ultimately, if you get the average, suppose lambda is equal to 10 and probability of lambda is 1 by 10. So 10 is divided by 10 multiplied by 1 by 10, that is 1. So rate is 1. 1 is what? 1 is one customer per unit time. This is very important here. Otherwise, this point rate, this is rate. Rate means suppose lambda 1, lambda n is this is lambda n is 10. Lambda means 10 means this is a rate. Rate means per unit time. Per unit time. I have also explained this idea that when the quantity becomes rate in our not here in this semester, but sometimes in second semester or third semester, I remember that I explained this point that when quantity becomes rate when it is associated with unit of time. Whenever we say lambda is equal to 10, it is not a rate. But whenever we say lambda is equal to 10 per unit time, or unit time means per hour, per half an hour, per 2 hour, per day, immediately lambda n becomes the rate. So rate means it is associated with time. Suppose this is lambda is 10 per unit time, and you say the Pn is, for example, I'm saying you will get some exciting result, and Pn is 1 by 5. 1 by 5. So if you multiply this, what you will get? You will get 2. You will get 2. 2 means this is the what? Suppose this is only, and similarly you get another case. For this case, you get suppose 1. So total is 3. Total is 3 means you are getting this 3. And this is what? Expected rate of flow out of the state. So expected rate of flow out of the state n means what? 3. 3 what? Expected means average. Average means what? Flow out of the state n means 3. What is the unit here? One is the time, another is the customer. So expected rate of flow out of state n means 3 customers per unit time, per hour, for example, per HR. Per unit time is HR. So 3 customers per hour. 3 customers per hour. This ultimately we are talking about the concept. So this flow is what? This flow, outflow or inflow, both are ultimately interpreted or it is understood in terms of the customers. So number of customers, when we talk about the balance equation, when we talk about the equilibrium state, you just do not just to be crazy of only the mathematical expressions, left is equal, right is equal, okay, this, I get this thing. No, no, no. You just go behind the logic. What is going on here? Physical significance of the logic of this mathematics. Mathematics is very simple. I think this is just equivalent to the standard 10th class standard mathematics if you look at here. But logic is very important here. So I mean to say average inflow and average outflow is approximately equal under the steady state, and this is the reason we get this balance equation. And very nice, if outflow is 3, what example we were giving, so inflow is also approximately 3. So as many persons coming, as many customers are coming, all are getting service. That's all. That one getting the service. As many as, so many as they come, they get the service. That's all. So this is a balance equation. Perhaps this is the backbone. This is a backbone of the mathematical structure. This is a backbone, and this therefore this is a balance equation. Balance equation because this is balance means standard equation, and balance because left and right, A and B is equal, therefore balance equation. But this is a standard balance equation through which we will discuss further. Now, from figure 1 we have state 0. Okay, we have started from 0, therefore we are going to discuss this very case for n is equal to 0. This is possible because we have considered in the figure n is equal to 0. You cannot have the objection about this. So balance equation C gives us what? Lambda naught P naught is equal to mu1 P1. I rush to the balance equation. I show you n is equal to 0. You look at here, n is equal to 0, lambda minus 1 not possible, P minus 1 not defined, this not defined, so this term is not defined. N is equal to 0, mu1, this is mu1 and this is P1. In the left, n is equal to 0, lambda not or 0, P is 0, and mu 0 and P 0. So look at here, look at, worth noting here this very point to be mindful. Here will be mu naught. Mu naught is not defined, so this term is rejected. Sorry, and this term is also rejected. So you are getting mu1, P1, mu naught, and P naught. And simply we are going to have this one. You remember this one. Okay, so from here P1 is equal to lambda naught upon mu1, lambda naught upon mu1 divided, and it is given. This is equation number 3. In the same equation, n is equal to 1. N is equal to 1. Let us go in hurried manner. N is equal to 1. So lambda 0, P 0, mu 2, P 2, lambda 1, P 1, mu 1, P 1. The same thing we have got here. You look at lambda 0, P 0, mu 2, P 2, and lambda 1 plus mu 1, P1 is common here. You can. We have value of P1 here. P1 substitute P1 from here, so P1 is substituted here. This is P1. If it is P1, so mu2 is here, P2 is here. This goes in the right hand side. We take P naught, mu naught, this part as a common, So this will be -1 because of this, and mu1 is divided, it divides lambda1 and mu1. So this is division, and if you simplify this, mu2 p2 is equal to lambda0 upon mu1 and p0. This will be 1, so 1 will cancel 1. This is lambda1 and mu1. So lambda1 mu1 and this lambda0 is here, and this is p0. So p2 is this part. P2 is equal to lambda1 into lambda0 and mu2 and mu1 a p0. You just look at this, is also very interesting. 2 is here, this 2 is here. Then in the numerator, we start lambda1 and we come to the lowest one, and lowest is lambda0. And 2 is here, so 2 is here, and mu1 is here. This is the lowest value. This is the mu2 is here, highest value. So in the denominator, this is the, you try to get the rhythm. We are going to have the rhythm. This is in the rhythm with this. This is also in the rhythmic with lambda1. Rhythmic means this is 1 less than 2. This is also rhythmic, and this is also rhythmic. This is also rhythmic, and this is also rhythmic. Okay, and this mu2 and mu1 is also rhythmic, and lambda1, lambda0 is also rhythmic. And this is a similar quantity. It is coming as it is in each value. So now this is enough. Twice. Now what we say, recursive iteration. Recursive means next time we will substitute the value of p2, and the next expression for n is equal to 2, that will involve p2. We will substitute the value of p2, making the same thing and using the induction method. Induction method is what? When once we assume that for n it is true, expression is true, then it must be true for n plus 1. If it is true for k, it must be true for k plus 1. And by the induction, we get the expression Pn is equal to lambda n minus 1. You look at here, the same rhythmic situation is here. N is here, lambda n minus 1. And last is lambda naught. This is the lowest. N is here, then you start from mu n and mu n minus 1, and last is mu 1. P naught is as it is. Condition n is greater than 0. If you want to write n is equal to 0, you do not like this, then you can replace this condition. I have no problem. N is greater than 1, n is greater than 2, not greater than, so forth, so on, so forth, so on, so forth, so on, and so forth. This is also way of writing, but this is small and very beautiful. But now here question arises that how we can compute the P naught. This expression is not complete, because we are not given so far the P naught. If P naught not given, then find the value of P naught. So P naught, how we can value of P naught? P naught, all the probabilities. When we compute all the probabilities, what is happening? The P naught plus P1 plus P1 plus P2 and plus Pn plus Pn plus Pn plus so forth, so on, plus so forth, so on, is equal to what? Is equal to 1. So we want to have the value of P naught from here, P naught, and therefore P naught is what? 1 minus sum over n is equal to ranging over n is equal to 1 to is P1. So P1, P2, P3, computing P1, P2, P3 all, we can subtract from minus 1, we will get the value of P0. So this expression, remember this expression, this one, in the this big bracket, this is called, this expression, F is known as probability distribution for general Poisson Keywing model. Look here, nothing seems to be like Poisson. Is it here Poisson? Directly e to the power minus lambda, lambda to the power minus n, e to the power minus lambda, lambda to the power x upon factorial x, or like this. It is not like that. But this will be very exciting. This will give the probability expression for all particularized Keywing model, all special models. Then we will see the Poisson expression we can see. Then if it is not Poisson expression, then why we are saying Poisson? In the beginning, we have assumed that intervariable times follows the exponential distribution. Arrival follows the Poisson distribution. And if that is the assumption, then this rule is derived out of the assumption, and therefore it is called a probability distribution for general Poisson Keywing model. So this expression, balance equation, the transition diagram, they all are very important. We will derive the other derivations. With the help of this, you will surprise many of derivations we are going. So I think today it is enough. We will, if you have any questions, you can ask. We will meet you on Thursday again. So by that time,